we are discussing signal distortion on optical fibers. So, first we discussed what is called dispersion, which is essentially the pulse broadening as the pulse travels on the optical fiber. Then we went to another aspect, that was attenuation, and then we saw there are various mechanisms by which the pulse energy is lost when it propagates on the fiber. So, we saw a mechanism which is the intrinsic mechanism by what is called the material absorption. So, when energy travels in the medium, like any other medium, glass also absorbs energy. So, the pulse amplitude goes on reducing as it travels on the fiber. But more severely than that, we saw that inside an optical fiber, there are some kind of micro centers which are created, which have a refractive index slightly different than its surrounding, and that causes a loss, what is called the scattering loss. And we saw that the scattering loss is a very strong function of the wavelength. So, it goes as lambda to the power minus 4. That means, every doubling of the wavelength, the scattering loss reduces by a factor of 16. Now, these two losses are present inside the optical fiber even before the fiber was commissioned into the system. Once the fiber is commissioned into the system, there are two more additional losses take place, and they are what are called the micro bending losses and the radiation losses. So, we saw micro bending loss is the loss where if the fiber is deformed over micro scales, then locally some leakage of energy takes place, and that loss is called the micro bending loss. Now, another loss which is of importance is what is called the radiation loss, and that is if the fiber is gently bent over a large arc, and if the radius of that arc is much larger compared to the wavelength, then you have a leakage of energy, and that is what is called the radiation loss. So, let us understand, when the fiber is gently bent, why the radiation takes place from the optical fiber. So, first let us consider the fiber which is the straight fiber. So, if you have a fiber which is straight like this, then the mode propagates inside this, and the phase fronts are perpendicular to the axis of the fiber. So, you have the phase fronts which are parallel planes like that. So, when the energy travels inside the optical fiber, every point on this phase fronts travels with the velocity, which is the group velocity or the phase velocity, depending upon whether we are considering pulse or you are considering continuum signal. But important thing to note here is that every point on this phase front moves with the same speed. However, now if I gently bend the fiber, then the fiber becomes an arc like that. So, this is the fiber now, and now the phase fronts are again perpendicular to the direction of propagation, but direction is now become along this arc. So, the phase fronts are no more parallel, but they are like the fan which are pivoted to the center of curvature of this arc. So, you have phase fronts which will look something like this, something like this, something like this, something like this, and so on. So, in the first case, when the fiber was absolutely straight, the phase fronts were parallel to each other, whereas when the fiber is bent, then the phase fronts move like a fan which are pivoted to the center of curvature of this arc. Now, when that happens, every point on the phase front now does not move with the same speed, because the points which are closer toward the center of curvature, they move with the lower velocity. As you go farther and farther, the velocity increases, and very soon you will reach to a region or used to a distance where the velocity becomes equal to velocity of light intrinsically in that medium. And beyond that, then the velocity cannot increase. So, as a result, the energy which is beyond that distance, that cannot propagate along with this mode now. So, that energy slowly detaches itself and starts leaking from the structure. This is the one which is what is called the radiation loss. So, important thing to note here is that no matter how gentle the bend is, you will always find a distance at which the velocity will try to become greater than the velocity of light intrinsically in that medium, and the energy will leak out. So, now the two things to observe here, that when I consider a bending loss, and let us say if I consider a modal distribution which is something like this. This is the distance at which the velocity becomes equal to velocity of light in that medium. What that means is that this now energy which is in this region showed by this hatch region, that energy cannot propagate along with this mode, because it requires velocity greater than the velocity of light in that medium. And then this energy will essentially detach and will contribute to the radiation loss. Now, since the energy which is leaving from here, since the mode has to be maintained like this, as soon as this energy is lost for continuity of the fields, again the fields have to be generated. So, power is drawn from the power which is flowing inside the fiber. So, there is a net loss of power which is going to take place in the energy which is flowing inside the core of the fiber. Now, since this is the energy which is going to be radiated, the amount of energy which will get radiated will depend upon how close this distance is from the core, and secondly, how spread this field is inside the cladding. The first thing is very clear, that as you bend the fiber more and more, the radius of curvature will decrease, and because of this distance will come closer and closer. So, sharper you bend the optical fiber, more will be the radiation loss, because closer will be this distance and this energy will go on increasing. Similarly, if I consider a mode whose field is much spreaded inside the cladding, then for a given bend, more energy will be radiated, because you will have more electric field amplitude beyond the distance at which the velocity becomes greater than velocity of light in that medium. And we know from our modal analysis that as you go to higher and higher order modes, the more and more field now is inside the cladding. So, what that means is, for a given bend, higher order modes will suffer more radiation loss, because their field is going to be more spreaded inside the cladding, and lower order modes will be least affected. So, the important thing which we get from here is that whenever we consider a fiber, and if the fiber is bent, then the energy is going to leak out from this, and sharper the bend, more will be the energy loss from that bend, and higher the mode, more will be the energy loss for a given bend. However, one can calculate this. The analysis is not very trivial. You have to do some very rigorous analysis to calculate what is called the radiation loss. And what can be shown is that this radiation loss is a very strong function of this radius. So, if you bend the fiber very gently, and if the radius of curvature is of the order of tens of centimeter, the radiation loss is practically negligible. But if you consider the radius of curvature of the order of about few centimeter, then this radiation loss increases very rapidly. So, if one wants to avoid the radiation loss while laying the fiber, one should make sure that the fiber loops of the size of few centimeter should not be formed, otherwise one would have a very heavy radiation loss. This also gives us something interesting, that if you consider a fiber which is straight and if there is no energy leaking from here because the mode is completely guided, one would never be able to tell whether the fiber is illuminated or not illuminated, because there is no leakage of energy, and unless the energy reaches to an observer from outside, one would not be able to tell whether the fiber is carrying light or it is not carrying light. So, if the fiber is kept in absolutely straight position, then looking at the fiber, one would not be able to tell whether the fiber is lit or not lit. But if you take the fiber and you bend it, then because of the radiation loss, the energy will start leaking, and then one can see the light emitted from the bend. So, by bending just the fiber, one can see the light coming out, and this light can be seen from outside if it is in the visible range, or can be measured from by an instrument if it is in the invisible range. But the important thing to note at this point is that if the fiber is bent, then energy can leak very easily from the fiber. Now, recall when we were talking about the characteristics of optical communication in very first lecture, we had said that optical communication is very secure. That means no data can be tapped when the information flows inside the optical fiber. What we however see now is that if you take a fiber and just bend it, the energy can simply leak from the fiber and the signal can be tapped. But in practical fiber, you always have the covering sheets which will not allow you to tap the light which is radiated by the bent fiber. So, if you had a bare fiber, then of course, as soon as the fiber is bent, the light will get emitted and there will be leakage of power. But if you consider a fiber which is having jackets and all that, then even the radiated light will not be detected and you still have a security in your communication. So, this is the important aspect whenever we lay a fiber inside a system, that fiber should not form very small loops, because if you do that, then you would have the excess loss over and above the intrinsic loss in the optical fiber. So, putting all effects together, then one gets the losses in a system which are much higher compared to what intrinsically an optical fiber is capable of giving. Also, you would note that when we go for a wavelength of 1550 nanometer, since at that wavelength the V number is smaller compared to 1310 nanometer, the energies, modal energy spreads much more in the cladding. So, all these losses have a higher contribution at 1550 compared to 1310. So, though theoretically we see that the attenuation for glass is minimum at 1550 nanometer and 1310 nanometer the losses are higher, in practice when the fiber is laid in the system, invariably we find that the losses at 1550 are comparable or higher than 1310, because these losses, the microbending losses and the radiation losses, they become large at 1550 nanometer compared to 1310 nanometer. Let us now turn back again to our discussion on the dispersion. That we saw that when we consider a dispersion in the single mode optical fiber, we saw that the dispersion comes because of two components. One is because of the intrinsic material dispersion, another one we saw is the dispersion which is because of the wave guiding nature. And we also saw that the material dispersion is not in your control, because once the material glass has been identified, practically the material dispersion is fixed. However, the waveguide dispersion, which depends upon the fiber parameters, the size of the fiber, the refractive index profile of the fiber, these quantities can be manipulated by changing the fiber parameters. So, what we now find interesting is that the total dispersion which we see on the optical fiber, which is always a combination of the material dispersion and the waveguide dispersion, that can be manipulated by controlling the fiber parameters. And that is a very interesting option, because if you recall, when we talked about dispersion and loss, we find that 1310 nanometer wavelength is the wavelength where dispersion is minimum, but the loss is about 0.2 to 0.3 dB higher. If you go to 1550 nanometer, then the loss is minimal there, but the dispersion is about minus 20 picosecond per kilometer nanometer. So, either you could operate at a wavelength where loss is minimum, which is 1550, but then you have a larger pulse broadening or lesser bandwidth, or you can operate at 1310 nanometer where the bandwidth is large, but the loss is higher. As we said earlier, for a good communication, we would like to get both. We should have a low loss and we should have a large bandwidth. So, in earlier situation, either you could get bandwidth or you could get the loss, because these two wavelengths 1310 and 1550, they were offering one at a time. However, once you find now the fact that the dispersion can be manipulated by controlling the fiber parameters, then immediately one can proceed to find out whether one can shift the zero dispersion point, which was at 1310 nanometer, to 1550 nanometer. So, if you could manipulate the waveguide dispersion, then there is a possibility that the zero dispersion point can be shifted to some other wavelength. And if that option is available, immediately one would like to shift to a wavelength which is 1550 nanometer, because that is the wavelength where the loss is minimum. So, if you could tailor the fiber such that the zero dispersion fiber for this wavelength for this fiber is at 1550 nanometer, then one can have both. We will have low loss and we will have a very large bandwidth, because dispersion will be 0. Precisely that's what essentially is done in what is called the dispersion shifted fibers. So, initially the fiber dispersion characteristic was something like this. This is the wavelength which is going from about 1200 nanometer to about 1700 nanometer. Dispersion goes like that. This is the wavelength which is 1310 nanometer, where the single mode optical fiber has zero dispersion. But now by changing the refractive index profile of the fiber and size of the fiber, we manipulate the waveguide dispersion such that this curve is shifted something like that, like this. So, now the zero dispersion point has been shifted from here to here, which is around 1550 nanometer. So, this fiber gives you both advantages. It gives you a low loss and it also gives you a large bandwidth, because zero dispersion point is shifted now to 1550 nanometer. So, this is one of the interesting fibers which is used in today's communication system, because that fiber essentially gives you the broadband characteristic at 1550 nanometer. When this is happening, that you could manipulate the dispersion characteristic to shift the zero dispersion point from here to here, the laser technology had improved significantly, and also the fiber technology loss performance also improved significantly. So, you had that peak which was there between these two windows of 1310 and 1550 nanometer. That window was slowly removed, that peak was slowly removed to get a very large window from about 1200 nanometer to 1600 nanometer. So, we had a very large low loss window now available, which was going from 1200 to 1600 nanometer. The lasers were available which could give sources at any arbitrary wavelength you like between 1200 and 1600 nanometer. So, only issue was, can we manipulate dispersion characteristics so that the dispersion remains low over this entire band from 1200 nanometer to 1600 nanometer. And precisely that is what the engineers did. They went and modified the profiles of the optical fiber and manipulate the dispersion characteristics so that you get dispersion characteristics something like that. Now, note here that when you have a dispersion characteristic something like this has a 0 dispersion point at 1550. It also has a 0 dispersion point at 1310. That means this fiber can accommodate all the old systems or old electronics which was operating at 1310 nanometer. It can accommodate all the modern electronics which is going to come at 1550 nanometer. And if need be, it can also accommodate the entire band between this 1300 to about 1600 nanometer. So, now you see, by designing this special type of fiber, what are called the dispersion-flattened fiber, dispersion characteristic is flat now and is very close to 0. You got a low dispersion flattened fiber, where effectively now the bandwidth is about 1300 nanometer to 1600 nanometer, about 300 nanometer bandwidth. This is now is the true wideband medium. So, note now, when we started with optical fiber, the bandwidth which was utilizable, the usable was very small, and by doing all these innovative things, essentially now we have got a fiber which has a bandwidth as large as about 300 nanometer. And if you recall, 1 nanometer is about 100 gigahertz. So, you have 300 nanometers. So, 300 into 100 gigahertz, that is the kind of bandwidth now this dispersion flattened fiber can offer. So, the dispersion profile essentially has become now very complicated. So, earlier when we had a single mode fiber, the dispersion profile was a step profile something like this, where this was N2 and this was N1. But now, if I talk about the dispersion shifted fiber or dispersion flattened fiber, for this the refractive index profile within the core, and note here this is the single mode fiber we are talking about. So, the core size is still of the order of about 6 to 8 micron. Within that, now we have got a refractive index profile which is extremely complicated. We can create a refractive index profile which could be something like that. Or we can create a refractive index profile which could be something like this. This size from here to here is that fiber core diameter, which is about 6 to 8 micrometer. So, as the technology has progressed, you can make now the fiber with a very accurate refractive index profiles, and you can create these extremely complex refractive index profiles within the core of the optical fiber, which has a size of about 6 to 8 microns, and that gives you a large flexibility in achieving the desired dispersion characteristics. So, the fiber technology and all these innovative ideas essentially has improved the dispersion characteristics of the optical fiber, and now we have got truly a very wide band medium which has a bandwidth of about 300 nanometer or 300 into about 100 gigahertz. So, in today's system, one does not see simple single mode fibers, or one may see variety of fibers. So, now let me just summarize what we have seen up till now. We started with a simple model on the optical fiber. We saw the fiber which was multimode optical fiber, and we saw that this multimode optical fiber is only of academic interest. Normally, dispersion of this fiber is very large. Then we said without sacrificing the launching efficiency or without reducing the core size too much, one could reduce the dispersion by making the fiber what is called the graded index optical fiber. And these are the fiber which normally are used in practice. So, in local area networks where data rate is not very large, the fiber which are used are the graded index optical fibers. And then we saw that if you go to very long distance communication, then the fiber which one has to use is what is called a single mode optical fiber. And single mode optical fiber has a zero dispersion intrinsically at 1310 nanometer. Then to achieve a low dispersion at 1515 nanometer wavelength, we modified the refractive index profile, and then we got another class of fiber what is called the dispersion-shifted fiber. And then to accommodate large number of wavelengths between 1300 nanometer and 1550 nanometer, we designed another class of fiber what is called the dispersion-flattened fibers. So, in today's system, essentially this all types of fibers are used depending upon what are the distances and what kind of bandwidth we are using and how many channel transmission we have into optical communication. One can, however, now ask a basic question that earlier when I had a fiber something like this, where I had core refractive index N1 and cladic refractive index N2, we define this quantity what is called the V number, which was 2 pi upon lambda into core radius into numerical aperture, which was square root of N1 square minus N2 square. But if we have a refractive index profile which is complex like this, what is N1 and what is N2? In fact, there is not a single core here. One can say you are having multiple shells. The whole thing is now we are calling as core from here to here. So, you have an inner region and then you have a ring around it and then ring around it, and so you have a multiply cladded region that we call as core, and then where the refractive index become constant, that essentially we call as cladding. So, first thing to note here is that there is no one N1, though N2 you may say is the refractive index of the cladding which is constant, but we do not know what is this quantity N1 now is. So, obviously, this parameter V number which you could define for this kind of refractive index profile cannot be defined for the refractive index profiles like this. So, one has to find another means of characterizing the fiber. We know that the fiber is still the single mode optical fiber, and if you look at the field distribution of the single mode optical fiber, we know that the mode which is propagating is LP01. So, it has a maximum at the center and then the field dies down monotonically as we go away from the center of the fiber. So, typically if you look at the field distribution of the fiber, the typical distribution, so this is the core of the fiber, field is maximum here, it goes like that and then it dies down something like this. So, this is the field distribution which is plotted, magnitude of E as a function of R for LP01. And we also know for single mode optical fiber, the V number is very close to about 2.4. One can then show that this field distribution which we have here can be very closely approximated by a Gaussian distribution. So, within few percent error, essentially you can find the variation of this field. It can be approximated by the Gaussian distribution. So, inside a fiber, essentially in a single mode fiber, this is the core which is now very small, and that is the field distribution which you have, which we can approximate by a Gaussian distribution. Then one can say where the field dies down to 1 over E of its maximum value, if I get that point. And if I measure that diameter is the effective width over which the field is confined inside the optical fiber. Or if I talk in terms of the power, since the power goes as mod E square, where the power dies down to 1 over E square of its maximum value, that is the point which you can call as the effective distance up to which the field extends. So, if I measure these 2 points where the field dies down to 1 over E of its maximum value, then you can calculate this diameter, and this diameter we call as the mode field diameter of the fiber. Now, in single mode optical fiber, the V number essentially used to tell us how the energy is distributed in the core and the cladding. And the distribution was a simple distribution. As I mentioned, it is very close to Gaussian distribution. Same purpose now can be served by this parameter, what is called the mode field diameter of the fiber. So, what we do, essentially we get the field distribution for the optical fiber. You measure the diameter over which the field reduces to 1 over E of its maximum value, and then that diameter we call as the mode field diameter. So, for a single mode optical fiber which has a complex refractive index profile, the mode field diameter is a much more meaningful quantity than defining the V number, because V number cannot be defined for these complex refractive index structures. Now, mode field diameter is an important parameter, because suppose we have different fibers and we want to combine this, because in any system you may not have only one type of fiber which can be running. Many times you may get fibers coming from different companies, different manufacturers, and you have to make a joint between these fibers. Obviously, if the light which is coming out of one fiber does not match with the other fiber in terms of its numerical aperture cone, then you will not have a guiding of the light efficiently from one fiber to another fiber. So, if I have the fiber which are of different nature, which have different refractive index profiles, which have different sizes, then how do I say whether these two fibers are compatible? So, one can show that if you make the mode field diameters of the two fibers same, then there is a perfect launching from one fiber to another, and there is no loss at the junction where the two fibers are connected. So, essentially whenever we want to make a joint between two fibers, without worrying about what are their actual parameters are, like what is the diameter of the core, what is the refractive index profile of the core, you simply ask only one parameter, and that is the mode field diameter of the fiber. If the two fibers have mode field diameter same, then they can be joined without a loss of light launching efficiency. And that's why this parameter is a very important parameter. The loss which takes place because of the mode field diameter, that is essentially given by the loss that is equal to 2 upon MFD1 upon MFD2 plus MFD2 upon MFD1. We can put in terms of the logarithm in terms of dB, So, I can take log10 like that. So, note here when MFD1 and MFD2 are equal, this is 1, this is 1. So, this ratio will be 1, log of that will be 0. So, you will have a 0 dB loss. Whereas, when these two diameters are not equal, then from here approximately you can calculate how much will be the loss at the junction when the two different kinds of fibers are joined. So, MFD is therefore one of the important parameters whenever we want to characterize now a single mode optical fiber which has a complex refractive index profile. Like this, there are many other parameters also which are required to characterize the fiber completely when the fiber is laid into the system. And another parameter which is of importance is what is called the birefringence of an optical fiber. So, we have another parameter what is called birefringence of a fiber. And this quantity is defined as follows. We have seen that if you consider the optical fiber, with a core which is absolutely circular, then we can launch a light which is linearly polarized, which can be decomposed into two orthogonal polarizations. So, let us say I have two linearly polarized mode, one has polarization like this, and other one has polarization which will be horizontal. So, if the fiber is absolutely circular, any arbitrary direction of the electric field can be decomposed into two. So, we say that we have two degenerate LP01 modes with perpendicular polarization, and since the fiber is absolutely circular, both the polarization see the same phase constant or they travel with the same speed. If that happens, then the state of polarization is maintained, because both of these fields are going to undergo the same phase change over a distance, and when they combine, again they generate the same state of polarization. However, in practice, the fiber is not absolutely circular. Because of the manufacturing process and so on, the fiber has small ellipticity. So, that means the effective radius which the vertical polarization sees is not same as the radius which the horizontal polarization sees. Or in other words, what we are saying is the V number which this polarization sees is different than the V number which this polarization sees. And since the V number changes, from the BV diagram we know that the phase constant also will change. So, that means we have the phase constants for two polarization for the same LP01 mode would be different. And if I define this phase constant by beta naught, as we have seen earlier, we get a quantity what is called the effective index of modal propagation. So, what this is telling you is that in a real fiber, the effective index for horizontal polarization and vertical polarization would be different. So, let us say that effective index is defined by Nx and it will be defined by Ny. So, due to a small ellipticity in the core of the optical fiber, the modal index seen by horizontal and vertical polarizations are not same. So, the difference in these two different refractive indices is what is called the birefringence of the optical fiber. So, we define this quantity birefringence, that is equal to Ny minus Nx. Now, what does the birefringence do? Firstly, it will be immediately clear that the phase constant of this polarization will be beta naught into Ny, and the phase constant of this polarization will be beta naught into Nx. And since omega by beta is the phase velocity, the phase velocity for this and this would be different. So, initially let us say we had a linear polarization launched inside the optical fiber, which could be decomposed into these two components. And you may recall, in linear polarization both the components are in phase. So, to start with, we have a polarization which will generate these two components which are in phase. As the signal travels on the fiber, this thing will undergo a phase change which is beta naught into Ny, and this thing will undergo a phase change which will be beta naught into Nx. And since Ny and Nx are not equal, essentially there is a phase difference between these two components now. And when there is a phase difference between the two components, the state of polarization is changed. So, if the phase difference between these two becomes 90 degrees, the polarization will become circular. Any other phase difference, you will get a polarization with the elliptical polarization. So, now what we see is that when the light propagates in an optical fiber in the single mode, then let us say this is the fiber, light is propagating in this. Here the polarization was linear when it was launched, let us say it was something like this. As it propagated along the length, slowly it becomes elliptical, then after a certain distance it becomes circular, because the phase difference has become 90 degrees. Again the phase difference will increase, so again it will become elliptical, and so on, and linear, and so on and so on. So, as the light travels along the optical fiber, the state of polarization will go on continuously changing. Distance over which this thing changes, that we call as the beat length on the optical fiber. So, we can define what is called the beat length. That is equal to 2 pi divided by difference in the phase constants, which is nothing but beta naught into Ny minus Nx. So, this is the distance now, the beat length, over which the phase difference would change by 2 pi. So, again the same polarization will be generated from that distance. So, because of this variation in the size of the core of the optical fiber, the whole lot of things happen, and one of the things which happens here is what is called the change in state of polarization. If I see in terms of the group velocity, the same thing will happen to group velocity also, that whatever pulse I launched inside this, the pulse energy will get divided into two polarization, horizontal and vertical, and the two will travel with different group velocities. So, you will see that there is a tendency for pulse to separate out because of this. So, if I take now a fiber like this, and if I launch an optical pulse, the pulse energy will get divided into two polarization, one is this, one is this. And as it travels, because of the birefringence variation inside the optical fiber, you will see that the two pulses will not reach at the same time on the other side of the fiber. So, there will be a difference in this, and again this phenomena is a statistical phenomena. So, you will not get a systematically this pulse is moving forward or this is going ahead. There will be some kind of a jitter, something kind of thing will be developed because of this, and you will have an effective broadening of the pulse because of this phenomena. This is what is called the polarization mode dispersion. And in fact, this is the dispersion which is becoming a bottleneck in the high speed communication. So, even if you could design the fibers which are having very low dispersions and so on, ultimate the limiting factor would be what is called the polarization mode dispersion. So, this quantity also is an important parameter. In normal system where data rates are very small, these factors do not contribute, but when we talk about the data rates of few gigahertz or 10 gigahertz, or try to increase the data rate beyond that, then essentially all these factors they start playing a role. So, we see now the dispersion, not only we have a material dispersion, intramodal dispersion, but we also have what is called the polarization mode dispersion inside the fiber. The another parameter which normally one defines for a practical fiber, which is what is called the cutoff wavelength of the optical fiber. Now, we know that when we talk about a single mode optical fiber, the V number should be such that only one mode propagates, and ideally it should be as away from the cutoff frequency of the next mode, which is the LP11 mode. Because if this V number is very close to the 2.4, then even with the small manufacturing tolerances, the LP11 mode will get excited. So, energy will get diverted to LP11 mode, and because of that you will have some kind of dispersion or pulse broadening. So, we want that your V number should be as away from the cutoff V number for the next mode. That is the requirement. So, if we define a cutoff wavelength is the wavelength where the next mode will get start exciting, which is the LP11 mode. How do we quantitatively measure it? So, there are certain standards which are defined for measuring the cutoff wavelength, and the standards are as follows. You consider about 2 meter long fiber and excite this fiber with a tunable laser source which can excite both the LP01 mode and LP11 mode in equal proportion. So, now I have a fiber which is about 2 meter length, and then you are exciting this fiber with a tunable laser source which can excite both the modes LP01 and LP11. Now, let there be a loop formed because of this fiber. So, this fiber loop is of the order of about, let us say, 3 centimeter. The light is launched inside this, which launches LP01 plus LP11 mode. Now, what we do is we measure the output power here as a function of the wavelength and measure the loss, essentially a decrease in power, change in power, as a function of wavelength. So, let us say, suppose I measure the loss as a function of wavelength lambda. If I go to very small wavelengths, then both the modes are well excited inside the optical fiber. They are well confined inside the core, and even with the bend in this loop, which essentially would normally give a radiation loss, since this both the modes are well inside the core, the radiation loss is negligibly small. So, you will see most of the power appears at the output. So, the loss is very small. As you increase the wavelength and as you reach to a wavelength where now the LP11 mode is approaching cutoff. If this mode approaches cutoff, then its energy spreads more in the cladding, and because of this loop now that energy is lost very quickly, because we saw that as you bend, if you are having more energy inside the cladding, there will be more energy loss for that. So, as you increase the wavelength where the lambda becomes close to the cutoff wavelength of LP11, you will see there will be loss of energy corresponding to LP11 and the loss here will increase. If I go to a wavelength still further, then LP11 will not get excited at all because it will be below cutoff, and then the whole energy will be launched into LP01 mode, which will not have a loss inside this loop again, and you will get almost the full power coming here. So, if I look at now the typical loss profile, it will look something like this. So, initially you had the low loss because both modes were well guided inside the core. Then as you go reach to the cutoff frequency, the loss increases because energy corresponding to LP11 mode is radiated away. And when I go on the other side, still longer wavelength, LP11 does not get excited at all. And since the energy is confined to only now LP01, most of the energy again appears here. So, standard says if you get this profile, this longer wavelength where the loss now is 0.1 dB with respect to this. So, this thing is 0.1 dB. That wavelength is what is called the cutoff wavelength of the optical fiber. And typically, if you take a 1310 nanometer fiber, the cutoff wavelength will be about 20 to 30 nanometer away from the wavelength of operation. So, this is one of the important parameters whenever one specifies the fiber. The fiber now is specified by various parameters. It can be specified by its mode field diameter. It can be specified by its dispersion characteristics. It can be specified by its cutoff wavelength. So, whenever we specify a fiber from the manufacturer, these are some of the parameters which one has specified, so that you can get the required fiber. So, here what we have done is we have essentially seen the general characteristics of optical fiber, and then we have now got certain parameters on the basis of which fiber can be specified, like the mode field diameter or the cutoff wavelength or the dispersion or the loss and so on. So, this more or less covers the discussion on the optical fiber, the basic propagational characteristics of the optical fiber. So, next time when we meet, we talk about other issues related to optical fibers like manufacturing of optical fibers and so on, and then we will go to the other topics in this course like the optical sources and other things.